Hi, I'm Andrew Kramer, and this is a short video on my work in radar state estimation and mapping for MAVs in dense fog. I'll first cover the weekly supervised training procedure I used for the learned radar noise filter. First, radar scans are spatially aligned with LiDAR scans. We can see an example of this here with the radar points in red and LiDAR points in green. Then, radar points within a threshold distance of the nearest LiDAR point are labeled as keep, and the rest are labeled as discard. We can see an example of labeled radar points here with keep points in green and discard points in red. I then used these labeled point clouds to train the point net segmentation network. We can see here the results of the trained network classifying a live stream of radar points. Again, keep points are colored green, while discard points are red. The labeling seems reasonable subjectively, but the real demonstration of the learned filter's efficacy comes when it is added to the radar mapping pipeline. This next clip shows my radar mapping pipeline without the learned noise filter. It is important to note the output octomap is very sparse. It often highlights salient obstacles, but these obstacles are difficult to distinguish from noise. Additionally, there's very little persistence in the radar map. These two properties severely limit the usefulness of radar maps using this method. They could perhaps be used for local obstacle avoidance, but this system would not be useful for higher level tasks like global planning. This clip shows the same radar mapping pipeline with the learned noise filter added before the octomapping node. This mapping system provides much more dense and detailed octomaps. It captures salient obstacles and often highlights the floor and ceiling as well. This is far more useful as a robotic mapping system. Next, we compare the radar mapping system to visual and LiDAR mapping. We can see vision and LiDAR provide denser and more detailed maps, but the environment represented in the radar map is still easily recognizable. The situation changes when fog is added to the environment. Visual and LiDAR mapping methods are severely handicapped by the fog, but the radar mapping system is completely unaffected. Lastly, I show my full state estimation and mapping pipeline in action. We show the sensor rig pose, which is estimated by integrating the velocity and orientation estimates from my radar-inertial state estimation system. We also show the raw radar returns for reference. This clip shows my state estimation system is sufficiently accurate to provide short-term relative pose estimates with low drift, and the mapping system reliably identifies obstacles in the environment. That's all for now. Thank you so much for your time, and I hope you found my work interesting and useful.